Hello, this is Jack Jackson. This is the start of a new playlist. In this playlist, we're going to be talking about Chapter 11 of my notes, Circle Theorems. So, in this chapter, we'll be examining theorems related to circles, including relationships among arc measures, measures of central and inscribed angles, and lengths of chords. The derivation and proofs of these relationships are all found by finding a pair of congruent triangles or a pair of similar triangles. Um, so these are another good application of these basic triangle tools that we've been using throughout the course. So again, we can see that um, these triangle um, things, these triangle results, particularly congruent triangles and also similar triangles, those results are some of the core building blocks of doing lots of kinds of geometry. Now, some of these results might be true in other geometries, but we're just not going to worry about that. Our study is this chapter, in fact, for pretty much the rest of the course, is all going to be restricted on to Euclidean geometry only. So let's start with some basic definitions. Some of these we've seen before, but let's review them and maybe add a couple of new things here along the way. A circle is a set of points in a plane which are a fixed distance from the fixed distance called the radius from a fixed point called the center of the circle. A circle is named by its center with its radius as a subscript or just by listing its center. For example, we might say circle C like this, or we can use this symbol, circle C, which of course you can copy and paste from this if you have my uh, document here, but it's also found under the equation symbols. Let's see, here they are. And let's see if I can find them. I think it's under operators. I think I'm using that symbol right there, or maybe I was using this one here or there. I'm not really sure what the difference is, maybe in the size, but this one here, for example, I think is the one I used. Okay, and that's a circle with center C. It's not determined what the radius is if you say that. But if we do this symbol here and then put a subscript with an R there, right there for a subscript, that's a circle with center C, but its radius is R. Okay, notice that C is a point and R is a number. R is a positive number, actually. The set of points in a plane in the same plane as a circle, whose distance from the center is less than the radius, is called the interior of the circle. And the union of a circle and its interior is called a circular disk, sometimes spelled with a C instead of a K. The set of points in a plane whose distance from the center is greater than radius is called the exterior of the circle. And so then a circle partitions a plane into three disjoint sets: the circle, the interior of the circle, and the exterior of the circle. By the way, notice that in a plane is an important part of the definition. If we allowed it to be in three-dimensional space, then that would be but let the rest of the definition alone, that would be a sphere. Continuing on, so far really not a lot new except maybe the notation here. A line segment with one endpoint on a circle and the other at the center of the circle is called a radial segment of that circle. The length of the radial segment is called the radius of the circle, and a radial segment is a line segment set of points, and the radius is a distance measurement, a positive real number. Now, some people use the word radius as double duty, both as the line segment, or what I'm calling a radial segment, and a number, its length. I prefer not to do that because I want to make a distinction between a set of points and a number. And I think, I mean, sometimes there's not too much confusion if you know from the context, but I'd rather do it this way to make it more just more cleaner. A line segment with both endpoints on a circle is called a chord of that circle. C-H-O-R-D, chord. A chord of a circle containing the center of the circle is called a diametric chord. The distance, which is twice the radius of the circle, is called the diameter of the circle. So D equals 2R. where d is the diameter, r is the radius. So notice that the length of a diametric chord is the diameter of the circle. A diametric chord is a line segment set of points, and a diameter is a distance measurement, a positive real number. Once again, it's kind of the same thing that we had with the word radius and radial segment. Here we have diameter and diametric chord. Some people use the word diameter for both the diametric chord and for the distance. I'm going to make a distinction between those two things. Continuing on, a line intersecting a circle in 2 points is called a secant line to the circle. A line intersecting a circle in exactly 1 point is called a tangent line to the circle, and we say the line and the circle are tangent to each other. We also say that the line segment or ray are tangent to a circle if and only if they are subsets of a tangent line and they intersect the circle in exactly 1 point. 2 or more coplanar circles are said to be concentric if and only if they have the same center. Similarly, 2 or more spheres are concentric if they have the same center. You know what? Let's don't even worry about spheres right now. We'll may come back to studying some spheres later. A central angle of a circle is an angle whose vertex is the center of the circle. Let A and B, you know what? Let me go ahead and illustrate some of these. I was going to illustrate them at the end, but I'm going to go ahead and illustrate some of these as we go along. So I have a sketch GeoGebra thing here that just has a circle and some basic things. So here's a circle. So you have a couple of basic circle tools. You can create a circle by specifying a point for the center and another point on the circle like that in GeoGebra. Or the other way you can do it is you can do it by a center and radius. So you can click on here and then specify a radius, let's say 5 units. And that when you specify that, that could be some other variable or a slider or something like that that you have already created. So for example, just to show you, we could have a slider here. Now it needs to be positive. Say like that. Call this radius. I'll just leave it like it is. We'll leave the name the same. So this could be the radius here, and we could then do a, what is that, S sub 1. Okay, so then I could go by circle with center and radius, click here, and then just say S sub 1 here, and now that center, that is controlled by that radius. That radius is controlled by that slider. Okay, so let me look at, here's a radial segment, and the radius is the length of that segment. Over here we have, it's 8 at the moment. We can make it larger or smaller by moving the control point. I think you can probably see that I made this one by center and point. We can also use a compass tool here, and the compass tool is you click on a distance here, and that makes a circle of that radius, and then you just have to specify the center point. For example, using the compass tool, if I click on this distance and click here, that's going to be a circle centered at B. It's going to go back through A. So there's a little bit of a quick overview of some of the most basic, just basic circle tools. Okay, so once again, here we have the circle. The circle is simply just the points here, the blue points, not the point A, not the center point. These points in here are the interior of the circle. The points out here are the exterior of the circle. And so, for example, if we do a line segment here between 2 points, let's see right now, what's our radius? The radius is about 8, just a little bit bigger than 8. So, for example, I can measure the length of this. Here pretty quickly. Let me just have it label its its value, which is its length. Okay, and so notice if that length is less than 8, less than the radius, these are all points. This point D, D1. These points are all in the interior. If it's exactly equal to 8, right, 8.01 or whatever, then it's on there. If it's bigger than the radius, then it's in the exterior. So all these points here where this distance is more are in the exterior. Notice that the exterior is unbounded, but the interior is bounded. Okay, so here's some other things that we've already talked about. First, here's a chord. A chord is just a line segment with both endpoints on the circle. If that chord also contains the center of the circle, that is a diametric chord. And of course, the length of that diametric chord is the diameter of the circle. And of course, that's just twice the radius. So if you double that, you get that. There's some rounding off here because things aren't, these numbers are both rounded off, but this is twice that on the radius. Okay, let's go back to our definitions now. Let's see. Okay, so I think we're kind of caught up there. Next, a line intersecting a circle in 2 points is called the secant line to the circle. A line intersecting a circle in exactly 1 point is called a tangent line to the circle. And we say the line and circle are tangent to each other. And so let's take a look at that. So here's a tangent line. And notice that it just touches in exactly 1 point. One thing interesting that we're going to be able to prove at some point is that if we do a radial segment to the point of tangency, check out this angle here. Pi over 2, that's pi over 2 rounded off. That's a right angle. In fact, that's how I constructed the tangent. I just made a point on the circle, made the radial segment, and then say make a perpendicular line. So there's a tangent line. Here's a secant line. The secant line goes through 2 points on the circle. See that? So in a line in the plane is either going to go through the circle in 2 points, 1 point, or not at all. Like this line here misses the circle altogether. There's some point right in here where it's tangent, and then it's 2 points, 2 points, 2 points, 2 points. Somewhere over here it's tangent again, and then then it doesn't intersect at all. Okay, next, let's just keep going with our definitions. 2 or more coplanar circles are said to be concentric if and only if they have the same center. So let's illustrate that. Here's a concentric circle. It's just another circle with the same center. If I move the center around, they both move. Could be larger, could be smaller. So those are concentric circles. A central angle of a circle is an angle whose vertex at the center of a circle. Look at that. So here's a central angle. Of course, like any angle, it is the union of 2 rays with a common endpoint. The common endpoint just has to be the center of the circle. These are the points that control that. And then we have this minor arc. This minor arc is intercepted by this angle. So we have this central angle here, and the intersection of the circle with the interior of the angle, well, You take the union of the angle and its interior and intersect that with the circle, and you get this arc. It's called a minor arc. Okay, so it's always the interior of the angle. Here, let's go ahead and that angle should be measuring in between 0 and 180 degrees, but 0 and 0 and between 0 and pi radians. So the arc measure of that angle of that arc is the angle measure of this central angle. See the 0.96 radians, 0.96 radians. It'll be measured in radians or possibly in degrees. It's an angle measurement. Contrast that with arc length, which is the length of this, as if you were putting a tape measure around here. Those are not the same thing. Here we're just based, the units are based on, there's somewhere under here, there's an underlying grid like this, and this unit is one distance length from 0 to 1. And so if you were to take a ruler, take a piece of string, for example, and go around this, and go be real careful with that, not stretch it, but just follow the path, cut that string off, and then straighten the string out and lay it along here, it would go to 5.86 about here. Okay, does that make sense? So from 0 to about 5.86, take a string of that length and it will follow along this path exactly. That's an arc length. Okay, so that typically will have some sort of unit to it, which is a length unit, inches, centimeters, feet, meters, something like that. Whereas arc measure is an angle measure, that's going to be radians or degrees. And really radians is a unitless measurement, so we usually don't put a unit on the arc measure when we're measuring in radians. Now, these are not the same thing. However, there is a nice relationship. If this radius is 1, okay, 1's pretty small here, then these will be the same. Okay, and this turns out to be, so as I'm moving this, the arc measurement is not changing, but the arc length is. This is a much bigger arc length than, say, here. Well, the relation, if we call this arc length S, which is a typical letter for that, and this angle, well, here I've got an alpha, then a more typical measurement would be call it theta. Okay, then we get S equals R times theta, where R is the radius. So we get a nice difference there. So this is what's called a minor arc. Here's the definition of that. Let A and B be 2 points of a circle C such that the line segment AB is not a diametric chord, I should say. The intersection of the circle with the interior of central angle ACB is the union of points A and B, and the union with points A and B is a minor arc AB of the circle, and notice the notation there. AB with the little curvy thing on top. The measure of minor arc measure, okay, is the measure of the corresponding central angle. So in other words, the measure of arc AB is the measure of angle ACB, where C is the center of the circle. And again, we'll typically measure in radians. Again, although one could use degrees. The set of points on a circle that are not part of the minor arc AB. Okay, let me copy that. Minor arc AB of the circle. Union with A and B is known as the corresponding major arc AB. Okay, so let's look here. So now this part here that you can see, well, here's the major arc. It's going to be the pink part. So the pink part here This is arc L. Both of these are arc LM. So that's a little confusing. Which one are we talking about? Well, if it's not stated otherwise, we mean the minor arc. So if you just see LM with the little curvy thing over the top, that's going to be arc symbol. That's going to be LM. The minor arc here, the maroon one, the red one here, and then the pink one going around this way would be the major arc LM. So you'd have to say major arc LM. Or since B's over here in uh, along this path here, we might call this arc LBM and use 3. Or if we put a point here, D1, this could be arc LD1M or arc MD1L. So notice that doesn't have to be exactly in the midpoint. It could be over here closer to one side or the other. Okay, so we have a major arc and a minor arc. You put those two together, they make the full circle, and the only place they overlap is the endpoints. The endpoints are in both of these arcs. Okay, so A and B are the endpoints of minor arc AB and of the major arc AB. Notice that both the minor arc and major arc are continuous portions of the circle. We'll also use a notation ACB with the arc symbol over it for arc AB, where C is the point of the arc not equal to one of the endpoints. And this may help to specify whether it's the minor arc or the major arc, like we just saw in the illustration, with the same endpoints. Now, we're also going to extend this notation a bit to include allowing things like this, the arc symbol with A1, A2, A3 up to AN, to indicate an arc that goes from A1 to AN, but the points A2, A3, 4, 5, whatever, up to n minus 1, A sub k are on the arc for natural numbers k from 2 to n minus 1, such that if you take successive ones like 1 to 2 and you intersect that from the arc from A1 to A2 intersect with the arc from A2 to A3 only intersects at A2, and the arc A2 to A3 only intersects arc A3 to A4 only at A3, and so forth. Okay, or more generally, arc AK to AK plus 1 intersected arc J, A sub j to A sub j plus 1, where I is not equal to j, is either the empty set, they don't overlap at all, or they only consist of one common endpoint. We can define M to be the midpoint of arc AMB if and only if the measure of AM equals the measure of MB, and of course the measure of AMB is then twice the measure of arc AM. Now this is very similar to the notation that we use for betweenness relationships in line segments. So the notation A-B-C, remember, indicates that B is between A and C, and our definition of that was that A, B, and C are collinear points, and AB, that distance plus the distance from B to C, equals the distance A to C. The notation for arcs using several points is similar to our notation for multiple betweenness relationships like this, A1 A2 A3 so forth up to AN, for several points on a line segment, say from A1 to AN. It's a very similar type of relationship. However, be careful that we don't use the word between when we're talking about points on an arc, because we have a formal definition of what between means. It's kind of interesting in mathematics. We use everyday words like between, but once we give them formal definitions, they take on a very specific meaning within the context of the study. In our case, the study of geometry, the word between has a very specific thing, very specific meaning, and it's only used when we're talking about points on a line, right? And a relationship there. So we cannot say when we have like arc ACB, we cannot say C is between A and B. If C were between A and B, that would be A dash C dash B. That would mean that A, B, and C are collinear, and that's impossible for a circular arc ACB. Of course, any 2 points on the circle could have a line through them, but not 3. In Euclidean geometry, circles are not straight. So, however, notice that we could have a relationship analogous to the relationship for line segments, since the measure of ACB is measure of AC plus measure of CB. But just as A dash B dash C does not mean that B is the midpoint of line segment AC, remember that. That is not the midpoint. Then when you say ACB arc does not mean that C is the midpoint of this arc. Now, here's something unfortunate. I want to show you something here. Suppose I want to make one of these arcs. Say I want to make arc, EF. Well, if I want to make line segment EF, it's pretty simple. You go here, you go to insert an equation like that, and then you go to equation here, go to accent, and you can make it a line segment like that. Okay. Well, what if we want, what if we want to make arc EF, right? We should be able to do the same thing, right? Let's try that. Go to this. Go to insert an equation. Go to here, and then here's the problem. None of these are that one's close, but it's not the same. None of these are the proper arc symbol that we want. That is unfortunate. Okay. But what I was able to do, actually, I use another program called MathType, and I created this thing in MathType, or if you use LaTeX, you could do that. And I created this symbol there, and then I converted that to Word format, Word equation format. So if I were to read arc EF, what I would do is I just copy and paste this, and then now it is editable, and I can, go back in here and say EF. If I wanted to make one of the, if I want to make this E sub 1, I could still go to here, select equation, go to a subscript like that. I can use the equation editing tools to edit this thing just like I would normally, and it keeps the correct symbol on the top. If I want to add a point, somewhere on this arc, EVF, like that. Remember, I can't use the word between, but somewhere on that arc, like that. I can do that. So, if you're in my class, you'll have access to this document. You can just copy that, paste it. You're going to be having to type a lot of these this week in your homework sets and different things. So that's going to be something you want to do. Again, we define the arc length of a major or minor arc to be the measure in radians multiplied by the radius of the circle. Once again, note that the measure of an arc is a measure of a corresponding central angle measured in radians. Okay. This is different than the arc length of the arc, which is a length measurement. The arc length of the arc is consistent with taking a tape measure and measuring the arc with the tape measure. Arc length and arc measure are numerically the same for a particular arc if and only if the radius of the circle is 1. Since we're using radians for measuring angles, the measure of an arc is a radian measurement. Recall that radian measures are actually unitless measurements, so no units written down. Arc lengths are length measurements, so they should have some length units, centimeters, inches, whatever. Typically, they won't have a unit in GeoGebra because they're just assuming it's the same unit as the grid in the background. Given a circle and a diametric chord, the intersection of a circle and the closed half plane determined by the line containing the diametric chord is a semicircle. The endpoints of the given diameter are the endpoints of the semicircle. Semicircle is also an arc of the circle and has a measure pi. Corresponding arc of a circle, the rest of the circle, but include the same endpoints, is also a semicircle. So if we put our diametric chord here, there's our diametric chord. And if I just make it go like this, let's see if I can match up the same points. Then both of these arcs, the red one up here and the pink one down here, are both semicircles, and they both include the endpoints with some endpoints of a diametric chord. Okay. We have several more things here as well. Okay, now next we have just a few more definitions that we're going to look at right now. An angle intercepts an arc if the endpoints of the arc lie on different rays of the angle, and except for the endpoints, every point of the arc lies in the interior of the angle. Okay, notice this includes the possibility that one endpoint of the arc is at the vertex of the angle. So let's take a look at that here. Um, Actually, I don't really have one here. Let me make an angle here. So there's a ray and another ray. Okay, so this intercepts. I'll tell you what. Let's actually do this as well. Let's do an intersection of this and this and this and this. Okay, and so this arc going from whatever point this is here to this one here, F something to G something here, this arc is intercepted by this one. Even if the vertex is here, then the arc here is intercepted. See, that's in the interior of the angle. If you flip it around this way, then this major arc is intercepted. You can even have an angle that intercepts two arcs, right? So this angle here intercepts an arc here and another arc here. Both of those turn out to be minor arcs. Okay. You can't intercept three arcs, but you can intercept two arcs like that. Okay. The angle might might be a central angle, in which case the arc that it intercepts has an arc measure the same as the measure of that central angle, but you could have other things like this. You could have an angle that looks like this, where this point is here and intercepts an arc here. It could be basically kind of tangent like that and intercept the arc. So there's lots of different things, but it's the intersection of the interior of the angle and the circle. That's going to be an intercepted arc. Okay. Now we can also have an inscribed angle. Let's go ahead and look at the formal definition of that. Okay. An angle is inscribed in an arc if the angle intercepts the arc and the vertex of the angle is on the circle. Okay, so let's look at that picture. So here's an inscribed angle and intercepted arc. So here the vertex is on the circle, and then we have an inscribed arc there, right? So this is it's an inscribed angle. You have an intercepted arc. Remember, we could have it intercept the same arc without the vertex being on the circle. For example, we could have a central angle here. Where's the minor arc? So here's a central angle for a minor arc. Let's have it sort of intercept the same one. We could have the central angle intercepting this arc, and we could have this inscribed angle intercepting the same arc. Okay, so that's an inscribed angle. That does include the possibility of an inscribed angle where this is tangent to the side like that. And so this is still an inscribed angle there where it's tangent. And we have an intercepted arc. Okay, just a couple more and we'll be through with our basic setup. Two circles are internally tangent circles if and only if they intersect in exactly one point and their interiors have a non-empty intersection, and they're externally tangent circles if they intersect in exactly one point and their interiors have an empty intersection. Internally and externally tangent circles are just tangent circles, if you put them more generally, have a common tangent line. That could be called a common external tangent or common internal tangent, respectively. So we're looking at this here. Here are some internally tangent circles. So notice that the interior of this circle, circle Z, intersects with the interior of circle A and has some points in it, including the point Z, for example. But the two circles intersect at only one point, W here, okay, and they have a common tangent line, which is this line here that's going through W. Those are internally tangent. These are externally tangent, could be at the same point or a different point. So the externally tangent ones, again, have a common tangent line, but the interior of this circle out here and the interior of this circle don't have any points in common. So the circles have exactly one point in common, and they have a common tangent line. Okay, and so those were the, so here's some of these together from that same thing. Okay, so let's talk about a couple other things here that are related. Notice that an arc turns out to be a continuous curve, and it's a subset of the circle. We measure the arc measure of this arc by measuring the corresponding central angle in radians. So, let's see, what about this illustration? I think we've already talked about all of this here. We have a minor arc here, and then the major arc here. The measure of this minor arc is the same as the measure of this angle here, and the measure of this major arc is 2 pi minus the measure of the central angle, measure of the minor arc. The arc length is the radius, that length here, right now it's 8, times this angle here, which is here. There may be some rounding errors there. There's an inscribed angle. There's your internally and externally tangent circles. So I think we've come to the end of this video.